Good morning, all. I am Kiran Pachlasia, Assistant Professor at Sagar Institute of Research and Technology, Bhopal, the SAGE Group. Today, we are going to discuss on push-down automata from the subject Theory of Computation. As in previous video, we already seen about FA, DFA, NFA, and types of grammar. So now, let's move on push-down automata. Today, the topic on which we are going to discuss are push-down automata. It is also called PDA in short form. Components of PDA, structure of PDA, formal definition of PDA, terminologies related to PDA, and few examples. So we can start with push-down automata. A push-down automata is a way to implement a context-free grammar in a similar way we design DFA for a regular grammar. A DFA can remember a finite amount of information, but a PDA can remember an infinite amount of information. Basically, PDA is a combination of finite state machine and stack. Components of PDA are, there are three components in PDA: a input tape, a control unit, and a stack with infinite size. If we are talking about stack, so the stack head scan the top symbol of the stack. As we know, two operations are performed in stack: push and pop. With push operation, a new symbol is added at the top of the stack. With the pop operation, the top symbol is read and removed. A PDA may or may not read an input symbol, but it has to read the top of the stack in every transition. This is the structure of PDA, where we easily see this is the control unit, the input tape, and the stack. Formal definition of PDA. PDA can be formally described in 7 tuples: Q, sigma, S, del, Q0, tau, and F. Sorry. Q is the finite number of states. Sigma is input alphabet. S is stack symbols. S is stack symbol. No, S is the starting symbol. Del is the transition function. Q0 is the initial state. I is the initial top of the stack symbol, and F is the final set of accepting state, where F is an element of Q. The following diagram shows in a PDA from state Q1 to Q2 labeled as A, B tends to C, where A, B, and C are the input symbols. Here, B represents stack top symbol, A represent input symbol, and C represent push symbol. This means at state Q1, if we encounter an input symbol string A and top symbol of the stack is B, then we pop B, push C on the top of the stack and move it to Q2. Terminologies related to PDA are instantive description of PDA is represented by triplet Q, W, and S, where Q is the state, W is unconsumed input, S is the stack content. Then turnstile notation. A turnstile notation is used to connecting pairs of IDs that represent one or more moves of the PDA. The process of transition is denoted by the turnstile symbol. Considering a PDA where the 7 tuples are given, a transition can be mathematically represent the follow turnstile notation like P, AW, T, beta, turnstile notation Q, W, alpha, B. Here, this implies that while taking a transition from state P to state Q, the input symbol A is consumed and the top of the stack is T. Look here, that we are on transition from P state. The input symbol is A and the top of the stack is T, is replaced by a new string alpha. Note, if we want 0 or more moves of a PDA, we have to use the symbol for it. If a grammar is context free, we can build an equivalent non-deterministic PDA which accepts the language that is produced by the context free grammar G. A parser can be built for grammar G. Also, if P is a pushdown automata, an equivalent context free grammar G can be constructed where language G is equal to language P. In the next two topics, we are discussing how convert PDA to context free grammar and vice versa. There are two different ways to define PDA acceptability. First is final state acceptability. In this, a PDA accepts a string when, after reading the entire string, the PDA is in the final state. From the starting state, we can make move that end up in the final state with any stack value. The stack value are irrelevant as long as we end up in a final state. For PDA, the 7 tuples that are Q sigma as del Q0 IF, the language accepted by the set of final state is the string where Q0 W I tends to Q epsilon X, where Q is an element of F for any input stack string X. Second is empty stack acceptability. Here, a PDA accepts a string when, after reading the entire string, the PDA has emptied its stack. For a PDA, Q sigma S del Q0 IF, the tuples, the language accepted by the empty stack is the language where Q0 Wi tends to Q epsilon epsilon, where Q is the element of Q. This is known as empty stacks acceptability. Example, we have to construct a PDA that accepts the language over 0 power n, 1 to the power n, where n is greater than n equal to 0. So when we designing this PDA, the language accepted by this PDA, first of all, epsilon, because the value of n is greater than n equal to 0. So 0 is also accepted, and the language which this language created for this is 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. It means 0, 1, 0 before 1. Here, this is the example number of A and B have been the same number. Initially, we put a special symbol dollar into the empty stack. Then at the Q2, we are encountered input. Then the state Q2, we encountered the input 0 and top is null. We push 0 into stack. This may iterate. And if we encountered input 1 and top is 0, we pop this 0. Then at state Q3, then when we at state Q3, if we encountered input 1 and top of the stack is 0, we pop this 0 with the move epsilon. Then at state Q3, if we encountered input 1, top is, we pop the 0 with this epsilon symbol. This may also iterate. And if we encountered input 1 and top of the stack is 0, we pop the top element, whatever the top element is. If the special symbol dollar is encountered at the top of the stack, it is popped out and it is finally goes that the accepting state is Q4. It means the whole string is accepted by this PDA. Thank you for watching. In next video, we discuss about conversion context-free grammar into PDA, PDA to context-free grammar. Till then, stay tuned. Thank you.